This chapter focuses on liquids, solids, and intermolecular forces. So, if you spill something in space, outer space, I should say outside the Earth's gravity, no apparent gravity. If you spill, say, something like water, you get this floating, sort of oscillating blob. And why does this form? Well, it forms because of intermolecular forces. So intermolecular forces, these are attractive forces between molecules. So intramolecular forces, those are forces within the molecule. Intermolecular forces, these are between the different molecules. And these have certain effects. Like it's the reason why we have solids, liquids, and gases. Well, I should say why we have solids and liquids specifically. Because of the strength of these intermolecular forces causes the matter to form the condensed phase as a solid or liquid. So we have three states of matter: solid, liquid, gas. I know some people consider plasma to be a state. Plasma, for this argument, is a gas. Because we'll describe what the properties of these fluids are later, or the property of the matter is later. So, and generally speaking, solids are the most dense. Water is an exception to that, and liquids are kind of medium, and then vapors have the least amount of matter in them. Matter per volume, density. So looking at water, and water is the exception for the solid phase, at least the most common solid phase at an atmosphere of pressure. But generally speaking, though, there's about 1,000-ish times as much matter in liquid water as there is in water vapor, and at least in an atmosphere, and that's why air and whatnot, it's real easy to move your arms in air. But if you swim, I love swimming, but you can get quite a push from pushing yourself in the water. It's from that amount of matter that's there. And but you can see that liquid water and solid water is pretty close as far as density. I know that it's solid water is slightly less dense at this pressure, but generally speaking, compared to the vapor, it's much more dense, and we call solids and liquids the condensed phases because of this, among other things. So some properties of the different states of matter. Solids. Let's start with solids. Solids have relatively high density. They have defined shapes and defined volumes, and they're very strong intermolecular forces. So the forces between them. If you increase the temperature, you get to a point where so remember, temperature is kinetic energy. Higher kinetic energy, there's enough energy to break some of those forces between the solid particles, and then it forms a liquid. So liquid is still relatively condensed phase, but the molecules are moving more freely, and if you heat that up to a certain point, and then the liquid will boil, and then you have the vapor phase. In the vapor phase, there's the least amount of attraction between the particles. And so this tells you a few things. First of all, melting points and boiling points, these are measurements of how strongly attracted particles are for each other. So a higher melting point, higher boiling point tells you that the molecules have stronger intermolecular forces, so forces between them. So liquids, in general, they're pretty, they're contained, but they have the ability to move around. But liquids are also incompressible. So this is one of the things, like we have hydraulic lines. So gases, which you'll learn soon, gases are compressible. And if you ever changed the brakes in your car and gotten air in your brake line of your car, and you press on the brakes, there is much less of a hydraulic effect on that. So sometimes your brakes don't even work depending on how much air is in your line. How do you fix that? You bleed the brakes, and then you get rid of the air that way. But yeah, liquids are incompressible. And also, liquids have a constant volume, and they take up the shape of whatever container they're in. So, I mean, and this makes sense for like cooking. If I were to measure a certain amount of liquid, I expect that amount of liquid to be the same when I pour it into another container. It just has a new shape. That's all. Gases are the least defined of all the as far as their shapes. They fill containers whatever they're in, and they're moving around constantly, and they are compressible. So gases are compressible versus liquids that are not. So and gases have the least amount of density and the largest molar volume for all the states. The states being solid, liquid, gas. Gases are compressible, and gases fill the shapes of the containers completely. They have no set volume, no set shape. And as mentioned before, liquids are incompressible, gases are compressible. So that's where we have things like hydraulic lines, and your brakes on your car are a hydraulic line. Solids have the strongest amount of attraction between them, and there's two main types, a crystalline solid and an amorphous solid. Crystalline solid has a very set, organized structure. Amorphous solid has no complete long-range order, but many amorphous solids, they have a general crystalline sort of way it is, but it's not all complete a single crystal. They just have crystals growing in just different directions, if you will. So it's not like an amorphous solid is completely random. There tend to be a bunch of different crystals growing in just different ways, and no overall set of organized structure. Of course, you do find some really pretty crystals like diamonds, or you can have certain minerals like really fancy looking quartz or something like that. You have very pretty crystals that way. But generally speaking, most solids are amorphous. It's very rare that you get a crystalline solid. And these particles, they're solid. But when you increase the temperature, they can vibrate. So the molecules kind of move around, they bounce around, but there's still that strong attraction keeping them together. Also, generally speaking, solids are incompressible. So putting a force on them, they don't shrink very much. And the fact that the solids have their own shape, so when you put a solid into a container, it keeps its own shape. It's not like a liquid that fills the shape of its container. So I've already mentioned about the crystalline solids and amorphous solids. Most things are amorphous solids. So which state of matter is compressible? Gases are compressible. Phase changes. So and I mentioned before the melting point and boiling point. These are in general how strongly attracted the intermolecular forces are for that substance. So the stronger the forces, the higher the melting and boiling points respectively. But temperature is kinetic energy, average kinetic energy, and it gets to a point where the kinetic energy is stronger than the forces keeping the solid together or the liquid together, and then from that there will be a phase change. And the other way can go as well. So if you take gases and you cool them off, eventually the attraction between the particles is stronger than the temperature, and then the gas will condense. And the same thing with the liquid. If the liquid is cooled to a point, and then the solid starts to form because the attraction is stronger than the kinetic energy of the liquid, then the liquids freeze. So, and generally speaking, water's an exception, but solids tend to be more dense than liquids, and liquids are more dense than gases. And I mentioned the phase changes already. Gases, so when you open up, so you have something like a liquefied propane tank. If you open up the tank, the propane is going to start to escape, and it lowers the pressure in the tank. So here is the diagram showing liquid water, which is the best describes the vapor. So vapor, it's still, you're not going a chemical change, it's a physical change only. And you still have water, H2O water, but it's now in the vapor phase. So you don't have it atomized, you don't have it turn into oxygen and hydrogen. So intermolecular forces are very important in regards to structure. So what the attraction between two different particles, it's electrostatic in nature, specifically electronic. So the unlike charges attract an electronic field. And we already mentioned there the strength of the intermolecular force is determined if it's a solid, liquid, or gas, and it's also temperature dependent. And the different types of attractive forces depends on the shape and structure of the particles. So we'll talk about this soon. We talk about with the different type of forces in between them. And the stronger the attractive forces on a particle, the more they resist in moving. So that's kind of like the law of inertia. If you study physics, the object at rest tends to stay at rest, kind of thing. So, and no material completely lacks particle motion. So everything is moving. So it's even at absolute zero, there is still some motion. Maybe for single atoms at absolute zero, there's no other types, but there's still rotational and vibrational energies associated with particles. And well, I guess even for a single atom, you have uncertainty in its position with the Heisenberg uncertainty principle. They've shown this even for larger things like small crystals. There is some uncertainty in their position even at absolute zero. So it's interesting. But that's more of an extreme case. More things tend to have vibrational, rotational energies at absolute zero, just no translational kinetic energy. And so I already mentioned the first point there several times. Repetition, I suppose. Repetition. And at room temperature, the moderately strong attractive forces result in materials being solids or liquids, so the condensed phases. And I already mentioned that melting points and boiling points are a measurement of the attractive forces. So why are molecules attracted to each other? What is it? So we've mentioned unlike charges for ions, but and that's a relatively strong force. So ionic compounds tend to have very high melting and boiling points. Polar molecules tend to have lower melting and boiling points than ionic compounds, and the molecules that have permanent dipoles, polar molecules, these tend to have higher melting points and boiling points than nonpolar molecules. We'll talk about a specific type called hydrogen bonding. It's a particularly strong type of intermolecular force. So the larger the charge difference, the larger, in terms of for the ionic bonds and also for the dipole bonds, stronger the charges, you have a stronger attraction. Also the distance. So as you move particles further away, this is just Coulomb's law. So that makes sense. However, these attractive forces are small relative to the bonding of the atoms. Yeah, because intermolecular forces tend to be weaker than intra, so within the molecule, intramolecular forces. And so if you look at an example for water here, water actually has a pretty strong bond between it, but if you look at within the molecule, the oxygen-hydrogen bond is about 96 picometers, versus between two water molecules about 300 picometers. The closer bonds, remember this, the closer bonding is, generally speaking, they're stronger. So the bonding within the molecule is significantly stronger than the bonding between molecules. So the simplest type of attractive forces is known as dispersion forces. So sometimes these are called London forces, sometimes they're called London dispersion forces, sometimes they're called dispersion forces. So you might hear these called different things. And these have to do with just the temporary induced dipoles between atoms and or molecules. So atoms, things like noble gases. And permanent dipoles are slightly stronger, and these have set charge differences in the molecules. And hydrogen bonding is a dipole-dipole force, but it's given its own category because it's particularly strong. So starting with dispersion forces, think of a very large, something like a xenon atom, a large electron cloud. And then as the electrons, say two xenon atoms approach each other, what happens is there is a repulsion from the electron cloud of the other, and because of that, the electron cloud of one xenon atom will shift away, but suddenly you have a slightly negative end of the atom and a positive end of the atom, and so now the two atoms will actually have a weak charge, a weak attraction between them. And this weak attraction is known as the dispersion force. And every single molecule and or atom will have it. And it's temporary, it's induced. It just has to do with the delocalization of the electron cloud. And so here shows between two helium atoms, for instance. And you have that induced dipole, and you have a slight attraction to them. And how big it is, this charges depends on a few things. How polarizable the electrons are. So the bigger the electron cloud, so xenon is going to have a bigger polarizability than helium. So because xenon is a much larger atom, much larger electron cloud. And also larger molar mass, so as a molecule increases in mass, it's going to have a larger electron cloud, which means stronger interactions. And the shape of the molecule, so the higher the surface area, so the flat kind of molecules, these tend to have much more contact versus the spherical molecules. So imagine a frisbee and a basketball, both, and then on the floor, say that it's kind of like Velcro, and like you have the opposite type of Velcro on the floor versus the frisbee versus the basketball. Which one's going to stick more? And the answer is the frisbee, because there's more surface contact. And the same thing is true with molecules. When you have the flatter molecules, there's going to be more traction between the molecules than the more spherical ones because of the surface area. So here is this chart shows the relative masses on helium to xenon, and as a molecular mass increases, the boiling point increases, and that's to do with the polarizability. And with this, I might add, helium, there is some argument saying that helium is only found in a vapor phase. So the distance between solid helium, for instance, solid helium, I'm trying to use the mental quotation marks, is about 5 angstroms. And because of the huge distance between it, there is not really that much of an attraction between helium atoms, even in a solid phase. So it's debatable if helium has any phase other than gas. But that's an advanced topic. But again, I try to inspire you to study more. And I already mentioned this, as the molar mass increases, the electron cloud gets bigger, and then the strength of it, the strength of this dispersion force increases, which means a higher boiling point. And now the shape of the molecule, mentioned the frisbee versus the basketball. So these are the same molecules, they're just isomers, and the flatter molecule is stickier than the spherical one. Therefore, the flatter molecule has more surface area, higher dispersion forces, higher boiling points. And also just the size of the molecule. So these are all the normal. So the normal means straight-chained hydrocarbons. And as the hydrocarbon gets more massive, the boiling point increases. So alkane is a hydrocarbon. So molecules that have only hydrogen or carbon in them. So that's what an alkane is, and all single bonded. So straight chains that we've already talked about. If you have branch chains, these have lower boiling points because of the less surface area. So it has to do with the surface area argument, where the straight chains ones, these have the most surface to area contact, where the branched ones, I'm going up to the spherical ones, have less, and therefore there's less polarizability. So which halogen has the highest boiling point? It's the heaviest one, iodine. So talked about induced dipole. How about permanent dipoles? So many molecules, as you've learned in previous chapters, are polar, which means the molecules always have a separation of charges between them. And this means there's going to be stronger attractive forces between them. So dipole-dipole forces are stronger than the induced dipole. There's still an induced dipole with them, but it's overshadowed by the fact that there is just this permanent separation of charges in the molecule. And then because of that, it is a relatively stronger intermolecular force, so the forces between the molecule. And because of this, it takes a little more energy to separate them, and because of that, there tends to be higher boiling points and melting points. So, as mentioned before, that is a measurement of how attractive the particles are for each other, is the boiling points and melting points. So, looking at formaldehyde and ethane, they're both about 30 grams per mole, but notice that the boiling point and the melting point is significantly higher for the permanent dipole formaldehyde than it is for ethane. And if you look at this chart, you have the boiling point on the y-axis and the strength of the dipole moment on the x-axis. And it's easy to see the general trend is the greater the dipole moment, the higher the boiling point. So that means higher attractiveness between the particles. And solubility affects this. So like dissolves like, meaning polar will dissolve polar, nonpolar will dissolve with other nonpolars, but polars tend not to mix with nonpolars. And there are hydrophilic, so the word hydrophilic, that means water-loving groups. So hydroxyls, CHO, that's an aldehydic group. C double bond O, that's COOH, that's a carboxylic acid. An amine group and a chlorine group. These are all water-loving. Hydrophobic groups, so these are water-hating. And carbon, hydrogen, and carbon-carbon. These tend to be the types of bonds that don't mix with water. And actually, the truth of the matter is, the hydrophobic groups don't necessarily hate water. They love water. Water has a permanent dipole, and the electron cloud is in these groups is much more attracted to the water than it is to themselves. But the thing is, the water has its own bonding, and as these hydrocarbons try to get into the bonding scheme of the water, water just pushes them out of the way. So it's actually the water is kind of the exclusive one rather than the hydrocarbon being afraid of water. So they prefer water, but water is the exclusive one in this relationship. And molecules, they can have both hydrophilic and hydrophobic parts. So they have polar and nonpolar. And these have various things. So these molecules can have various functions. So like the cell membranes, for instance, are phospholipid bilayers. So the phosphate group is hydrophilic, and the lipid is hydrophobic. And actually, a cell membrane is effectively just 2 molecules thick. You have the phosphate groups on the outside, and then the two lipid chains facing each other, and you form a very effective skin. So, lots of interesting things and applications in biology. Some liquids are immiscible, meaning they don't mix. So water and something like pentane, they don't mix. And it has to do with the different charges. And I mentioned before that actually the pentane is going to be more attracted to water than the other pentanes, but the water actually pushes it out of the way. It's because the water wants to keep its own bonding. But just by gravity, the water is more dense, so it goes further down, and the pentane is less dense, so it floats on top. So conceptual connection here. Acetylnitrile is polar. From this map, determine the geometry of halo 2 acetonitrile molecules interact with each other. So you're going to have the positive end and the negative end is going to be attracted to each other. So they're opposite ends of the molecules. So this is the first one. You're going to have them line up this way, where the opposite ends of the molecule, the negative end around the nitrogen is going to be attracted to the more positive end of the hydrocarbon, the methyl terminus group. And so for a specific type of bonding, hydrogen bonding, so when you have hydrogen directly, so this is only directly, hydrogen directly attached to an oxygen, nitrogen, or fluorine. And these molecules, these tend to have particularly strong dipole moments, and we have its own category to it. So we call this hydrogen bonding. And just because a molecule has hydrogen, oxygen, nitrogen, or fluorine in it, so it does not necessarily mean there's going to be a hydrogen bond. It's only if the hydrogen is directly attached to the oxygen, nitrogen, or fluorine. And this is showing the different attractiveness then between them. And if you look at water, for instance, water is unique. We'll learn about water. It's unique. Water can give and receive 2 hydrogen bonds. And water actually has a very high boiling point for its molecular weight. Other molecules can have hydrogen bonds, so you should here you see 2 ethanol molecules, and then along the bent OH group structure there is the attractiveness there, and you have the hydrogen bond there with the alcohol. So hydrogen bonds, these are relatively strong. They are in fact dipole-dipole, but they are given its own category. And substances that have hydrogen bonds, generally speaking, will have higher boiling and melting points than the similar substances that do not have hydrogen bonds. These are not as strong as intramolecular chemical bonds. So these are still intermolecular, and they're not as strong as the covalent bonds within a molecule. So if you look at this is an isomer. You have ethanol and dimethyl ether. So it's the same molecule, same atoms, but different connectivity. And you can see that there is a huge difference, well, especially with the boiling point. The melting point, not too much, but there's a huge difference in the boiling point of ethanol versus dimethyl ether. And what about the other groups, groups 4A and 6A? So hydrofluoric acid, water, and ammonia, these have hydrogen bonds, and they have higher boiling points than you'd expect. But for nonpolar molecules, such as hydrides of group 4, so that's carbon, and carbon and silicon going down, these intermolecular forces are due to dispersion forces. So they increase going down the column. And hydrides of groups 5 through 7, and these are not including ammonia and water and hydrofluoric acid. These tend to have both dispersion forces and dipole-dipole. So they're going to have slightly higher boiling points, but as we'll show, the hydrogen bonds are the ones that are going to have this particularly strong attraction. Then the strongest intermolecular force is the ion dipole. And the reason it's stronger is because the ion has the full charge. So you're dealing with a polar molecule like water. It's still a partial charge, partial being less than the charge of an electron or proton, which is 1.6 times 10 to the minus 19 coulombs. But for an ion has a full of that charge, so there's going to be a stronger attraction than between a full-fledged charged ion and a polar substance like water. So generally speaking are the dispersion forces. These are the weakest, and they're present in all molecules and atoms. So even things that have hydrogen bonding still have dispersion forces. And the magnitude of the dispersion force, these will increase with the molecular weight and also with the shape of the molecule. So the longer, flatter molecules have higher dispersion forces than the more spherical ones. Polar molecules have dipole-dipole attractive forces, and generally speaking, these are stronger than dispersion forces. And then hydrogen bonds, these are the strongest of the intermolecular forces that a pure substance can have. And hydrogen bonds are only when there's a hydrogen directly bonded to oxygen, nitrogen, or fluorine. Hydrofluoric acid is the only one that exists for fluorine, though. And ion dipole attractions, these are very strong. These are the strongest of the intermolecular forces, and these work when ionic compounds will dissolve into polar molecules. And then an ion dipole, these are important for things to dissolve. And actually, the ionic compounds, they tend to be the weaker ionic compounds, so the larger ions with a lower charge, because the stronger charges with the smaller ions, those tend not to dissolve. So actually, the fact that things dissolve show that's actually a weakened ionic bond as well. So this chart then shows the different strength of different types and different strength of intermolecular forces. So which substance is going to have the highest boiling point? It's the one with the hydrogen bond. And other things that come from intermolecular forces, surface tension. Surface tension is that liquids try to minimize their surface area. Some things have very high surface tension, some things have low surface tension. Liquid mercury, for instance, has a very high surface tension. So if you've ever seen liquid mercury, it has a very large bead versus something like water. And like I said, the surface tension tends to make particles try to be spherical. And the top layer of like a liquid, it will behave differently than so the surface is going to behave differently than the bulk material because there's nothing on the outside. There's nothing and there is then an attraction there between the molecules at the surface. And you can do certain things, like you can float like a paperclip, and there are some insects that can float on water this way as well. Use the surface tension of water to float. And these top molecules, these have fewer neighbors, therefore these are less stable. So, and then they have a higher potential energy. And the surface tension of a liquid, it's the energy required to release that surface area of a given amount. And for instance, look at water's surface tension. It's 72.8 millijoules per square meter versus C6H6, I guess it's going to be benzene, is going to be 28 millijoules per square meter. So some of the things that affect surface tension, stronger intermolecular forces. Stronger intermolecular forces, there's going to be higher surface tension. And increasing the temperature reduces the surface tension. Also, lowering the temperature increases the surface tension. So, and it has to do with the amount of kinetic energy, and then it's easier to stretch that surface when there's more motion. Viscosity. Viscosity is the resistance to flow. So maybe you've heard the term slow as molasses in January. So molasses is a syrupy sort of liquid, and January tends to be cold. So, and like a spoiler alert, temperature, low temperature increases viscosity, high temperature decreases viscosity. So resistance to flow. And the unit for viscosity is poise, or often centipoise. And water has viscosity of approximately 1 centipoise at room temperature. And the higher the attraction, the higher the viscosity. So that tells you molasses in January has a very high amount of traction between it versus other liquids. And you can see here that the higher molar mass, the higher the viscosity and the higher attractiveness before these normal alkanes there. And what affects viscosity? Stronger intermolecular forces. So same rules before. The flatter molecules are going to have higher viscosity. The spherical molecules with less attractive are going to have lower viscosity. and also temperature. So lower temperature means higher viscosity, and higher temperature means lower viscosity. So the old molasses in January. Another effective intermolecular force is capillary actions. So of course the tiny blood vessels that we have, they're known as capillaries, and the attractiveness between the blood and the blood vessels help pull blood away from our hearts with our circulatory system. It's also a game our body plays, because there can't be too much of attractiveness between the blood and the walls of the vessels. Otherwise, the blood will stick to the walls of the vessels, and then no blood will flow. So that is interesting. But we can see capillary action, like with drawing of blood. If this image here, if you stick a little bit of stick somebody in the finger, say, with a capillary tube, the blood will flow up the tube. So the narrower the tube, the higher the liquid will rise. That's capillary action. So this is a balance between the cohesive forces. These are the ones that hold the liquid molecules together, and then the adhesive forces. These are the attractiveness to whatever the tube is made of. And another hint: the tube's usually is made of glass. Plastic has a much less adhesive force for water. And seeing here, this image here on the right, you can see the more narrow the tube, the more the capillary action, the more the liquid is drawn up the capillary. So the smaller diameter. Meniscus, so this is also, it's similar to the capillary action, has to do with the attractiveness to the whatever container it is. And interestingly enough, so if you have beakers and test tubes made of plastic, they tend not to have a meniscus. Glass, on the other hand, so especially glass like the silica glass, that means that there's hydroxyl groups, OH groups, on the surface of them, and then water is very attracted to them, so it can draw up the water up the side of the container, and most glassware that you see in lab tends to be the Pyrex, the borosilicate glass. So if you compare it to other liquids like mercury, mercury is much more attractiveness to itself than to the silicates on the glass. Therefore, it beads up. And also, I mentioned before, if you have if you have plastic, which is a hydrocarbon, the water tends not to draw up that as much. Really, it's a very flat line, not much of a meniscus on plastic glassware, if you will. And the molecular dance, the dance of molecules in motion. Things are always moving, and there is temperature is translational energy, but things can still vibrate and rotate as well. So liquids are always moving around, and temperature is that average kinetic energy. So, but there's a distribution. There's a distribution of this. It's not just all the same. So, and this will come important when we talk about vaporization. So we've noticed that some liquids evaporate, and the higher the surface area, the faster the rate of evaporation. So liquids can evaporate. So we know this with water, you let it sit out, it will disappear and become a vapor. And thermal energy, so temperature is average kinetic energy. So you look at this image down here, and the y-axis you have fraction of molecules, on the x-axis you have kinetic energy, low temperature and high temperature, low temperature to the left in the blue, high temperature to the right in red. And you can see for the higher temperature there's a bigger fraction at higher energies. And the minimum energy to break the intermolecular forces is shown there in the dashed line, and the higher temperature has a higher fraction. Therefore, the higher the temperature, the more the liquid will evaporate. So it makes sense. And the opposite direction is condensation. So molecules lose energy by collisions, and then some of the molecules are of lower energy, and then they can turn to a liquid. And then this forms tiny liquid droplets, And this process of the vapor going back to liquid is known as condensation. And vaporization and condensation, they are opposite processes. And but if a container is open, the vapor molecules spread out faster than they can condense. So the vapor molecules just go out into the surrounding air. And so if a container is open, the net rate of vaporization is greater than the condensation. Therefore, there's a net loss of matter, and it looks like it disappears. But in a closed container, the vapor cannot go out forever, and it's stuck in the confined area. And then eventually you get to a dynamic equilibrium where the rate of vaporization, the rate of condensation is equal, and it looks like nothing is happening. So also, the weaker the attractive forces, the less energy it needs to vaporize. So we've mentioned this before with the boiling points. And then also, weaker attractive forces means more energy we need to remove from the vapor molecules before they can condense. So it's going to be harder to condense the vapor from there. And that means weaker attractive forces, the faster rate of evaporation, and these substances that are faster to evaporate are known as volatile. And so things like gasoline and fingernail polish remover reminds me of my childhood with my sisters painting their fingernails and taking them off. You could really smell that stuff. It's volatile. And things are non-volatile. So motor oil, for instance, this does not easily evaporate. So it has a stronger attractive force. So generally speaking, vaporization increases with increasing temperature, it increases with increasing surface area, and it increases with the decreasing of intermolecular forces. So which sample has the greatest rate of vaporization? It's the highest temperature with the highest surface area. So how does the energetics work in vaporization? So the high energy molecules goes from lost from the liquid, it lowers the average kinetic energy, so the temperature goes down. If energy is not dropped bound into the liquid, it will decrease. Therefore, vaporization is endothermic. So if it's at the same temperature and you have to break that bond between the liquid, and in breaking that bond, you have to put forth that energy, and that is known as the heat of vaporization, sometimes referred to as the latent heat as well. And then the opposite is true. Condensation is an exothermic process. And you might know this if you've ever gone into a steam room before. So steam room and sauna, you go into a steam room, you get hotter much faster than going to a sauna. The reason is because the steam room, the steam condenses on you and it releases that heat of vaporization, releases that latent heat. And then the temperature, then that energy goes into you very quickly. And vaporization in general requires energy to overcome the attractiveness. So we've mentioned this several times. So heat of vaporization, sometimes referred to as latent heat. This is the energy required to vaporize a liquid. And it's somewhat temperature dependent, but relatively constant. And heat of condensation is opposite that of heat of vaporization. Heat of vaporization is endothermic. Heat of condensation is exothermic. So think of walking in the steam room, or if you don't have been ever into a steam room, you can put your hand over boiling, like a steam as water is boiling, and that steam condenses on your hand. You can really feel that latent heat come off of the steam. So that's the exothermic going from condensation. So, and here's a chart showing different liquids with different heat of vaporizations at different temperatures, and also the normal boiling point. So, as I mentioned before, closed container, once the vaporization and condensation rate is equal, then the amount of vapor in liquid does not change, and this is known as a dynamic equilibrium. It looks like nothing's happening, but actually on a molecular level, there's lots and lots of things going on. So there's condensation and evaporation happening at the same time, but the rates are the same, and thus it reaches equilibrium. So this shows that picture. So A is initial with so it's like if you have an open container and then you put a stopper on it, eventually the equilibrium will shift, and then the equilibrium will be reached in beaker C, or I'm sorry, Erlenmeyer flask C. So, and this is known as the dynamic equilibrium. This chart here shows on the y-axis the rate and the x-axis the time. Eventually, the rate of evaporation and condensation reach each other, and then it goes to a dynamic equilibrium. You notice the rate of evaporation is relatively constant, and the rate of condensation, though, is dependent on the concentration of whatever is outside of it depends on the concentration of the vapor. So if this is a closed system, eventually the condensation, the vapor will reach a certain concentration, and then it'll stop changing. So that's what's going on with this image. So vapor pressure, vapor pressure is modeled by saying that at the surface of the liquid there's a pressure being exerted on the liquid, and also when the ambient pressure reaches the vapor pressure, the liquid will boil. So that's one thing with the vapor pressure. But the vapor pressure, I mean, that's one way to look at it. It's also, you can see there's various charts of them, especially with water. It's different for different temperatures. And generally speaking, the weaker the attractive forces, the more molecules will be in the vapor. And as we've said this before, the volatile substances. And the weaker the attractive forces, the higher the vapor pressure. So knowing that. And this vapor-liquid dynamic equilibrium, let's say we shift the equilibrium, we increase the volume of the chamber. So when that happens, the rate of vaporization will be higher, and then the amount of vapor will increase. Eventually, though, the vapor will accumulate, and then the rate of condensation will equal the rate of vaporization, and then equilibrium will be reestablished. And this image shows that, the dynamic equilibrium, and you can shift the equilibrium, and then eventually the equilibrium will reestablish itself, depending on the shift to the equilibrium. We'll cover this also more when we talk about equilibrium. This is a phenomenon known as, well, it's how equilibrium shifts. We'll talk about this much more in depth later, the shift of equilibrium. And dynamic equilibrium will respond to changes. And when a system is disturbed in equilibrium, the system will shift to counteract that change. So it's known as Le Chatelier's principle. So temperature dependence of vapor pressure. So as the temperature increases, the vapor pressure increases, and that's because the temperature increases. There's a higher fraction of molecules that have enough energy to break out of the liquid phase, and a small change in temperature can make a huge change in the vapor pressure. So that's one thing, and the vapor pressure depends on the strength of the intermolecular forces. So here you can see the vapor pressure on the y-axis in torr, and the temperature in degrees Celsius on the x-axis, and you can see the various charts or the various substances, and they can change. You can see how, and especially how the curve. It's a very curvy curve for this. So you get higher in temperatures, you can have a very big change in the vapor pressure with a small change in temperature. The boiling point: when the temperature of a liquid reaches the point where its vapor pressure is the same as the external pressure, then the liquid boils. So when the vapor pressure reaches the ambient pressure. And this is known as boiling. And the temperature which reaches the ambient pressure, that's known as a boiling point. Typically, we say normal boiling point. Normal boiling point is the temperature at 1 atmosphere of pressure, 760 torr. And but if you lower the ambient pressure, then the boiling point lowers. And you can see this chart here shows the various boiling points of water at different, in altitudes. As you increase in altitude in the atmosphere, the ambient pressure goes down. So you can see, for instance, in Denver, at about an elevation of a mile, the approximate atmospheric pressure is 0.83 atmospheres. Water boils only at 94 degrees Celsius versus at sea level is 100 degrees Celsius. So, and weather, of course, can change the ambient pressure as well. So let's talk about heating curves. So if you look at a liquid here, and the temperature is on the y-axis, and heat added is on the x-axis. And if you look at a liquid water here, it's going to, as heat is added, the temperature is going to go up, and then it gets to a point, and I can tell this is water because it's boiling at 100 degrees Celsius. Then the liquid starts to boil, and notice as the liquid is boiling, the temperature of the liquid does not change. So that's an important point for cooking things. So when you simmer something in water, it doesn't matter if you turn up the water, turn up the heat really hot. You can increase the temperature of the side of the container, but you're not going to increase the temperature of the boiling water. The boiling water is only going to be at 100 degrees Celsius at an atmospheric pressure. You can use a pressure cooker where you increase the ambient pressure. Then the water will boil at a higher temperature, but that's a different way of cooking. And then you can see you get the steam, and if you keep on adding energy to the steam, the temperature of the steam goes up. So you have, as the water is increasing in temperature, liquid water, the heat absorbed is the mass times the specific heat capacity change times the change in temperature. As the water is boiling, this is due to the energy going, it's not increasing in temperature, it's breaking the heat of vaporization. So it's doing that. And then once all the liquid is boiled, then the steam is then going by the same thing. The mass heat capacity, specific heat capacity times the change in temperature. So use this figure to estimate the boiling point of water and external pressure of 200 torr. So if you can see here, here's 200 torr, and come here to water. This is at 200 torr. This is going to be around 65, okay, 66 degrees right there. Clausius-Clapeyron equation. So this is known as a semi-empirical model. So semi-empirical, sort of experimental. You've been exposed to other models before, the quantum mechanical model for the atom. So the ideal gas law. Ideal gas law is a mathematical derived model. It is an idealized form. Now the Clausius-Clapeyron equation, this is a semi-empirical, sort of experimental. So Clausius and Clapeyron took a bunch of data and they played around with it, and they found out that the natural log of the pressure in millimeters of mercury and torr is the same thing as millimeters of mercury, the natural log of that, and if you relate that to the inverse of temperature in kelvins, that falls along a straight line where the slope of that straight line is approximately minus the heat of vaporization divided by R. So this semi-empirical model only works for the units natural log of pressure in millimeters of mercury and only temperature in kelvins. So this is bound by that specific set of units because this is just the model, and it was what they used to discover it. And it's just looking at tons and tons of data. You see this very, very frequently in engineering. You'll have semi-empirical models that work over certain parameters, and there are many semi-empirical models that you go through. Friction, for instance, at least the coefficient of frictions, those are semi-empirical models. That's not true friction. So the friction coefficients, that is a modeled from lots and lots of data. So you see this in other branches of science. You see this especially in engineering. So, and you're now being exposed to it in chemistry as well. Two-point form, so this is to get rid of the natural log of beta form, the y-intercept. You can take two equations and subtract them and come up with two-point form. And from this, you can use this equation to figure out one of the unknowns. If you You can look for a temperature or pressure, or also the heat of vaporization, so you can calculate that. So another thing to note on this is a model, so it is, since it's a model, it has some error associated with it. So this is not exact. So depending on what your application is, if you have to know the vapor pressure to a very exact amount, or the temperature to an exact amount, then this is probably not the best way to do it. You can do other experiments, but for something that has a tolerable amount of error, then the Clausius-Clapeyron equation is valid to do for that application. So changing topics, talking about we're going to talk about the plots of matter soon. So we'll first talk about there's a supercritical fluid called the critical temperature and a supercritical pressure called the critical pressure. If you're higher than the critical temperature or the critical pressure, the gas cannot turn into a liquid. Because of that, the gas, you can confine it to a certain area, but it's not really a liquid because liquids have attractions. But if you think of it this way, there's so much energy in the gas that it's not be able to form a liquid because it's moving too fast. But you put so much pressure on it that the gas condenses down to that would be sort of like the volume of a liquid. So that's what a supercritical state is. And actually, supercritical matter behaves differently than matter that's not supercritical. So some of the solubility rules, for instance, change. So you can get nonpolar molecules that dissolve in water, for instance, if you have supercritical steam. So here's a supercritical fluid where you have two states, but you get to a certain point where you sort of have one state, but it's not. It has sort of properties of gas and a liquid, but it's not really a liquid. The liquid-like state is more the density of it than anything else. Sublimation and deposition. So sublimation is going from solid directly to vapor, and then you can also have vapor go directly to a solid. This is known as deposition. So these occur at various specific temperatures and pressure. And because of this, molecular solids do have vapor pressure as well. So, and there are some solids at various pressures. So like dry ice, solid carbon dioxide sublimes, for instance. It does not melt. And I know this is fun because you can take dry ice and you can use it to make you can play like hockey with it. It's fun to play hockey with dry ice. Just don't touch it with your hands because then it'll freeze your hands. But it's fun to kick across the floor. So you can have solid water, for instance, can sublime. And this happens in your freezer. So if you wonder where freezer burn comes from, like if you get like a bag of peas and then suddenly there's a bunch of frost on the outside of your bag of peas, it's because the water is subliming and then condensing outside deposition outside of the material. So fusion and melting. So solids are heated. The molecules vibrate more vigorously, and then it can melt. So the kinetic energy of the molecules overcomes the attractiveness in the solid, and the molecule melts. And then the opposite is true. Going the opposite direction, the solid freezes. And so here's the heating curve for a solid. So you have, it's very similar to the boiling curve, where you have, and this is water again, so you have ice, and you heat up the ice. Eventually, so it increases by the heat flow is equal to the mass times the heat capacity, specific heat capacity times the change in temperature. And then you get to the point where the solid melts, and then the solid is melting at a constant temperature. And this would be true for a single crystal, but most solids are amorphous, so you tend to have a little bit of a curve there where the the higher energy surface tension ones melt first, and then the lower surface tension ones melt later. So you can have a bit of a, it's not going to be like a straight line block. It's going to have a kind of a bit of a curve on it. So that's for most substances, and unless it's a perfect single crystal, then it'll melt like it's shown in this picture here. But most things don't do that way. And and energetics of melting. So the high energy molecules are lost. It lowers the kinetic energy, and so because of that, melting is an endothermic process. So it takes energy to melt something. That's why we put ice into drinks. So we put ice into drinks. It's endothermic and it cools down the liquid. And the opposite is true. Freezing is exothermic. So frequently when you see things freeze, like a lake is freezing, it'll create fog over that, because then the energy from the freezing goes somewhere, so it vaporizes some of the water. So interesting that as the lake freezes, it also vaporizes some of the water. I always thought that was kind of cool. So, and the energy that it takes to melt is known as the heat of fusion. So sometimes known as the enthalpy of fusion. Enthalpy is H. So heat of fusion is endothermic, so it's positive. And the heat of crystallization is the opposite of it. So when things freeze, they release the heat of fusion. And generally speaking, it's much lower than heat of vaporization. Heat of vaporization is much, much higher. And to show you here, so what's the heat of fusion for various compounds, and also the melting points. Comparing this chart compares the energetics of heat of fusion. So it's a histogram with water, rubbing alcohol, acetone, and diethyl ether. And then on the y-axis, you have the heats of fusion or vaporization. And in the first block in blue is the heat of fusion. The second block in the red or pink is the heat of vaporization. And you can see that the heat of vaporization is much higher for every substance versus the heat of fusion. So here's the heating curve for water. And so imagine you take ice out of a freezer, and this is stage 1 in the bottom left corner, where it's cold ice, and then you heat it up, and then eventually the ice reaches 0 degrees Celsius. And the ice is going to melt, and it's going to melt until there's no ice left over. Now you have liquid water. Liquid water is going to increase in temperature until the water reaches the boiling point. I'm assuming at 1 atmosphere of pressure. It's 100 degrees Celsius. Then the water boils, and then you get to a point where the water is all steam, and then the steam can increase in temperature. So the steam, let me talk about some of the different properties. So I already mentioned about the melting point is actually going to be kind of a curve. And then the steam right at the as it's boiling, this is also known as saturated steam, or also known as wet steam, because that steam is if you touch it, it condenses and you get water. Yeah, it's wet steam. Then beyond 0.5, that is known as superheated steam, or also known as dry steam. So many places see dry steam. Dry steam is very dangerous. So because of it, because if you get hit by dry steam, it does not condense on you. And there are cases, so like Navy vessels and power plants frequently use superheated steam to turn their turbines, and Navy vessels to turn their propulsion systems to move the boats forward. And if there is a break and then the steam comes out, it can just vaporize people. It can vaporize parts off of people. And so it's very, very dangerous. Versus saturated steam, that's like if you go into the steam room and in a sauna. I'm sorry, not a sauna. In the steam room, I guess they're different things. If you go into a steam room, that's saturated steam. That's wet steam. You walk in there and then you get wet from the steam. Dry steam, on the other hand, like I said, it does not condense on you. It just really it can put out a lot of energy to you. So it's something to note with the different steams. Okay, so with this heating curve, and let's talk about the different points here. So point 1. This uses the heat flow equals mass times the specific heat capacity times the change in temperature. So if we start with 1 mole of ice at 18 grams, and then the specific heat capacity of ice is 2.09 joules per mole degrees Celsius. And for specific heat capacities, you can see it in various units. And for this, the unit Celsius and Kelvin are the same units. So they differ in magnitude, but by multiplication and division, Celsius and Kelvin are equivalent. And same thing with change in temperature. A change in Celsius equals the change in Kelvin. And so the heat of this stage for 1 mole of water is 941 joules. And then the heat of fusion is just a number of moles. So this is stage 2 where it melts. Then the amount of energy released here is 6.02 kilojoules. So remember the joules versus the kilojoules. So this is in kilojoules, and the previous one was in joules. Stage 3, heating up the water. This is equal to mass, specific heat capacity times change in temperature. And the ice was 2.09. Liquid water is 4.18 joules per gram degree Celsius. So the heat capacity changes. And then because this, well, you have a different heat flow. So this is 7.52 kilojoules. And the boiling is going to be the number of moles times the heat of vaporization. So 1 mole times 40.7 kilojoules per mole. So this requires 40.7 kilojoules of energy to do this. And then the last segment is the steam. It's the heat capacity, or the heat flow is mass times specific heat capacity times change in temperature. And the heat capacity, specific heat capacity for steam is 2.01 joules per gram degree Celsius. Okay, so the heat capacity for ice is 2.09. The heat of fusion for ice, when a small ice cube is at negative 10 degrees Celsius put into a cup at room temperature, which of the following plays a greater role in cooling liquid water? The heating of the ice or the melting of the ice? And from the previous example, you can see that the heat of fusion is the bigger thing. So that melting the ice is the bigger effect. So phase diagrams. So phase diagrams, we look at different states of matter in different conditions. These different regions represent different states. And the lines represent state changes where you have melting or boiling, for instance. And at these lines, both states exist. And then there's a triple point where you have all 3 states of matter coexist. And in most substances, the freezing point increases as the pressure increases. So water is weird. So water is weird, and the because of the fusion curve here is bent backwards. Most other substances, the fusion curve bends forward. And the reason for that is because at a low pressure, the more common ice is less dense than the liquid phase. There's other forms of ice. If you expand this chart, there's other forms of ice that are more dense than liquid water. So you can see this, and there are regions of the ocean where there's lots of ice on the bottom of the ocean. It's a different phase than the common ice, the alpha ice that you see at the surface of the Earth. But in this chart, you have pressure in the y-axis and temperature in the x-axis, and you have the 3 states of matter: solid, liquid, gas. And at a certain point, at a low enough temperature and pressure, only the solid and gas phases exist. And this is when the solid will sublime to a gas, or the gas will deposit down to a solid. And then you get to where the liquid exists. That's beyond the triple point. Triple point is where all 3 states of matter coexist. And then you have the fusion curve where the solid will melt or the liquid will freeze. And you have the vaporization curve where the liquid will boil or the gas will condense. But then you get to a point, the critical point, where the pressure and the temperature are too high. Then you have a supercritical fluid where you have various properties. It's sort of like a gas that's compressed down, but it can have different solubility properties in this in this state. So negotiating this, I mentioned some of these before. So A is known as an isobar, so same pressure. And isobar, you heat up the ice, so you can start off and move in that direction. You will melt ice, it will liquefy, and then it will boil. Point B is or line B is known as an isotherm, same temperature. In this case, as you decrease the pressure, you can then boil a liquid, and that's so you can this is how you make things like instant coffee, or you make instant orange juice. You take a liquid and you draw a vacuum, and then you boil off all the water, and you're left with the powdered coffee, powdered orange juice, or something like that, whatever it is you're making. So other substances. So you can see so on the top there's iodine. You have an isotherm for iodine, and then increasing the pressure, you can go from a gas to a liquid to a solid in that isotherm. But also notice that the fusion curve is pointed inwards versus pointed outwards for water. And you also have carbon dioxide here. You have an isobar at 1 atmosphere, and as mentioned before, carbon dioxide sublimes at a pressure 1 atmosphere. So you can play hockey with it, like we did in grad school. Fun times. So let's go to this. Substance has a triple point at negative 24.5 degrees Celsius and 255 millimeters of mercury. What is most likely to happen when a solid sample of a substance is warm from negative 35 to 0 degrees Celsius at a pressure at 220 millimeters of mercury? So the pressure is below the triple point, which means there's going to be a sublimation. So water is an extraordinary substance. So it's a liquid at room temperature, but it has a molecular weight of 18 grams per mole. So that's very light, but it's still liquid at room temperature. That's interesting. So it has, the reason for this is it has 2 hydrogen bondings. So ammonia has hydrogen bonds and only can give and receive 1, well, relative to the molecules. Water can interact with 2, though. 2 can react with the other 2. Water is a very good solvent, dissolves many ionic compounds and many polar molecules, which is good for nutrient transport, but it's also bad for pollutants. So you can transport, water is easily transported many good and bad things. And some nonpolar molecules have a little bit of solubility in water, like oxygen, like carbon dioxide. Although carbon dioxide does react with water to form carbonic acid, so it's a little more complicated for some of them. And it is a relatively high specific heat, so this has a moderating effects of places around water, and it also expands on freezing. So that's pretty weird. So that ice actually floats in water, and if you look at other liquids and solids, so things like olive oil. So if you put olive oil in your refrigerator, you'll see it freeze, and the frozen olive oil will sink to the bottom of the olive oil jar. So if you want to do that experiment at home, you can see that most solids actually sink in their liquids. So boiling points of the main group hadride. So compare it to water, and if you look at carbon and carbon family, this just increases up, and you can see that then you have ammonia, hydrofluoric acid, and water. This is because they have hydrogen bonds, so they have a little bit of a difference there. But water, of all those, has the highest, and it's because it can give and receive 2 hydrogen bonds. And thank you for listening, and please join me for the next chapter.